Okay, so you can still hear a lawnmower outside. That's several houses away even. It is just fantastically loud. So how are we going to compute the value of the sine of the arctangent of 4/3? Okay. Sine and arctangent are not inverse functions of one another, so I can't just say, oh, it's 4/3, hooray. That wouldn't make sense anyway, because the sine of something can't be 4/3. It's got to be between 1 and -1. Okay, so theta is an angle whose tangent is 4/3, specifically an angle in quadrant 4 or quadrant 1. So if the tangent is 4/3, which is positive, and I'm either in quadrant 4 or quadrant 1, which quadrant am I in? I've got to be in quadrant 1. So the tangent of theta is 4/3. That's going to be my y-coordinate over my x-coordinate. And if I relax having to be in a unit circle, I can then say the Pythagorean theorem gives me that the radius is 5. What I would normally do, by the way, is I always stay in the unit circle. Okay? I would just say that the y-coordinate over the x-coordinate is the tangent of the angle, which is 4/3. But we also know in the unit circle that x squared plus y squared must be 1. Cross multiplying here, we get 3y is equal to 4x, aka y is 4/3 x. I can then take that over here and get x squared plus 4/3 x squared is equal to 1. This gives me x squared plus 16/9 x squared is equal to 1. The common denominator being 9 gives me 25 x squared over 9 equals 1, from which I get x squared is 9 over 25. I'm trying to fit it in here, but I'm running out of space. So I'm going to come up to this top square, and I'm going to erase it soon anyway. So we end up with x squared is 9 over 25. So x is plus or minus 3/5 by taking a square root. But since I know I'm in quadrant 1, it's the positive one. Okay, so we would end up with x is 3/5. We would get y is 4/5. So in our triangle, we would have, down here at the bottom where I drew my triangle, we would have a 3/5 here. We would then solve for y and get 4/5, which is really just the same triangle the book draws scaled by a factor of 5. So if you want to always stay in the unit circle, it's doable. If you're comfortable going between circles of different radii, it might make your work a little easier. So in this example, using a 3 for the x and a 4 for the y, and then letting ourselves have a radius of 5, sure, there's no fractions. It's just nice whole numbers. Now, since I have an angle whose tangent is 4/3, this angle here, we can take the sine of that angle and use y over radius, which is 4/5. So, so the sine of that angle, 4/5. So the sine of the arctangent of 4/3 is 4/5. This is generally how we're going to do this sort of problem. Okay, figure out what quadrant you're in, build a triangle in that quadrant that produces the inner function, and then compute the outer one. So let's try it again here. Cosine of arcsine of minus 1/3. So arcsine says I'm in quadrant 4 or I'm in quadrant 1. If the sine of the angle is negative 1/3, which quadrant are we in? We have to be in quadrant 4. If I want the sine to be negative 1/3, I want the y-coordinate over the radius to be 1/3, but I want it to be in quadrant 4 so that this y-coordinate is actually negative. Okay. Sometimes I actually label the side as -1 just to remind myself that this is actually pointing down, understanding I'm not really saying the length is -1. I'm just saying it's of length 1, but it's pointing down. Okay, that's optional. You don't have to do that. You can just label it as a length of 1 and just remember that you're in quadrant 4. Okay, so now I have a triangle with my angle in it. The angle theta is arcsine of -1/3. It's an angle whose sine is -1/3. So now can you take the cosine of that angle? Sure. It's going to be the x-coordinate, which is positive because it's quadrant 4. The x-coordinate is positive, over the radius, which is 3. So 2√2/3. There it is. So the PowerPoint slide order got messed up, and it's jumped right to the answer. I was going to have you pause and try to work it out. So whoops. So let's just see the solution. So arc cosine of -1/3 says an angle whose cosine is -1/3. It's got to be in quadrant 1 or 2, because that's how arc cosine works. In which quadrant are cosines negative? Quadrant 2. So I know I'm a quadrant 2 angle. So then I need to label it to have cosine of 1/3. So we would put the x-coordinate to be 1. But since we're in quadrant 2, we understand that this is a negative, and the radius is 3. So now the cosine of this angle is negative 1/3. But then we just need to take the tangent of it, and tangent is just the y-coordinate over the x-coordinate. And just remember that this x-coordinate is actually negative. So 2√2 over -1 just gives me negative 2√2. Yeah, sorry, the slide order got all crazy here. But that's the solution of this one. Now, I can do it without a particular number. Okay, if this said, what's the cosine of the arc cotangent of 4? Okay, you could solve it using the same technique. What's the cosine of the arc cotangent of negative 1/3? You could solve it using the same technique. But just the cosine of the arc cotangent of u, where u is a variable. So you do the same basic thing, okay? Let theta be an angle whose cotangent is u. Okay, so the what am I trying to say? The range of arc cotangent is quadrant 4 and quadrant 1. The nice thing about quadrant 4 and quadrant 1 is that while the sine function, the y-coordinate, goes between positive and negative, okay, I know I'm in one of these two quadrants. While here I have y as positive, aka sine of theta is positive, and here I have y as negative, aka sine of theta is negative. No matter where I am in quadrants 1 or 4, the cosine is positive. Okay. Excuse me. So if I let theta be this angle, okay, we're just replacing cotangent, arc cotangent, sorry, of u with theta, and now I know this is going to be positive, okay, because the cosine of any angle is positive in quadrants 1 or 2. We can mark that as cosine theta times sine theta over sine theta, because then I get a cotangent of theta, not over, well, okay. I would say this is cotangent of theta times sine of theta. So here is your cotangent of theta times sine of theta. But instead of putting a sine theta in the numerator, they put a cosecant of theta down in the denominator. Okay. Because we do have a Pythagorean identity. The Pythagorean identity being that 1 plus cotangent squared of theta is equal to cosecant squared of theta. And if I take the square root of both sides, we get cosecant of theta can be replaced with this. Now, why would we do that? Because remember what theta was. Theta was the arc cotangent of u. So cotangent of theta is u. So wherever you see a cotangent of theta, you can replace it with u. So we just end up with a u over the square root of 1 plus u squared. So it doesn't matter what u was. All of this intermediate work, which is kind of confusing the first time you do it, I admit. Okay, at the end of the day, the cosine of the arc cotangent of u worked out to be this algebraic expression involving u. So let's see another one. Good, the book didn't give another one. So let's clear everything out here and just do another one manually. It really helps to see this done a couple of times. So how about instead of a cosine of arc cotangent, let's do the sine of the arc cosine. Okay, so I'm going to let theta be the arc cosine of u. Therefore, the cosine of theta is equal to u. Okay, so I'm just working with that inner thing and seeing what happens. Pardon me. All right. So what I really want to end up with is a sine of theta, because that's what I have up here, sine of theta. What I have is something involving the cosine of theta. What helps me relate sines and cosines to one another? The trig identity, sine squared theta plus cos squared theta is equal to 1. Since I want to get the sine of theta, I solve this as sine squared theta is 1 minus cos squared theta. And then I say sine of theta is plus or minus the square root of 1 minus cos squared theta. Okay. But what's cosine of theta? It's just u. So the good news is we've gotten our, and theta, remember, was arc cosine of u. So this is now the sine of the arc cosine of u. We do, however, have a plus or minus. Okay, so we need to be specific about which one we have. So let's go back to the beginning and ask arc cosine of u. What quadrant will that live in? Arc cosine always lives in quadrant 1 or quadrant 2. That's what it produces. In quadrant 1 and quadrant 2, what can you tell me about the sine function? It's always positive. Therefore, the sine of the arc cosine of something must be positive. So I take the positive square root over here. So the name of the game is use the trig functions you're given and find an appropriate Pythagorean identity that relates them to arrive at some sort of formula, but since the Pythagorean identities have all these squares in them, it's quite likely you're going to have a plus or minus square root at some point. How do you determine which one it is? You have to work through this quadrant argument. Okay, so we'll do one more. How about the tangent of the arc sine of u? So let theta be arc sine u. Okay? That means the sine of theta is u. At this point, since I know I'm going to be doing some quadrant stuff, we may as well ask, so arc sine lives in quadrant 1 or quadrant 4. What about tangent of something? Well, in quadrant 1 and quadrant 4, I see everything from minus infinity to infinity. So there's actually no specific plus or minus information here. Because the arc sine is going to produce something in quadrant 1 or quadrant 4, between negative pi over 2 and pi over 2, that's exactly one full period of the tangent function. It has all possible values. So let's just hope that things work out where I never have a plus or minus. So we've got sine of theta is equal to u. Okay, and what we know is sine squared theta plus cos squared theta is equal to 1. From which I get cos squared theta is equal to 1 minus sine squared theta. And we can do this. We can say cosine of theta is plus or minus the square root of 1 minus sine squared theta. And I don't know what's going to be important yet. I can't nail it down based on the information we have. Okay, but I could be a little bit more specific here, because notice we're not dealing with a tangent, we're dealing with a cosine. So since theta is the arc sine of something, it's in quadrant 1 or quadrant 4, and therefore cosine is positive. So because theta is specifically in quadrant 1 or quadrant 4, I can say cosine of theta is definitely the square root of 1 minus sine squared theta. So even though the tangent bit wasn't going to be specific, this intermediate step of cosine is. I need to clear out some space, so I'm going to erase the work on the left. Because this ended up not really going anywhere. It was all perfectly true. But the Pythagorean identity we used had to take advantage of the sine. Okay? Sine of theta being u meant I really only had one option for a Pythagorean identity. Thankfully, the cosine term is able to be specified as positive. So now, we're not trying to find cosine theta. We're trying to find tan of theta. Remember, up here at the beginning, we're trying to find tangent of arc sine u, which is what we called theta. But tangent of theta is exactly sine of theta over cosine of theta. So I have the sine of theta over the square root of 1 minus sine squared of theta. Because remember, we specifically did know that the cosine of theta was this positive square root down here. But notice sine of theta is equal to u. Right at the middle of the top there, we already remarked sine of theta is equal to u. Plug that in. U over the square root of 1 minus u squared. So there we have it. There is the tangent of the arc sine of u. It's always going to be u over the square root of 1 minus u squared. So you can figure out formulas like this for all possible combinations of trig function composed with inverse trig function. It's kind of important that the inverse trig function be on the inside for this technique to work. Okay, so hopefully doing a couple more examples made this more straightforward. Without having chosen homework problems yet it's quite likely that one of these will end up being assigned anyway. Just practice, work through them several times. Use the inner inverse trig function to define an angle. That gives you a trig function of an angle which has one particular Pythagorean identity associated to it. If you solve for the other bit, you're probably going to get a plus or minus, which should be able to be narrowed down based on the inverse trig function you started with, what quadrant you're in. Then use that new trig function. So in this example, right, we started off with the sine of theta, and now we have information on the cosine of theta. Once you have two different trig functions from a Pythagorean identity, you can figure out all of them. And so we reconstituted the desired tangent by doing sine over cosine. Okay, if we wanted to do, for example, secant, we would just do 1 over cosine, and so forth. All right, so that wraps up. There we go. That wraps up this section. So come on back for videos in the next section, which is 7.3, assuming 2 still comes after 3.